but you know, again, much of the material that I'm going to draw on here is going to be based on the McKinsey report. I will sprinkle in a lot of our, what do we got going on here? There is new software available. Just in terms of context, kind of thinking about what we have in terms of total emissions. Again, we've got this growth here in front of us between 2005 and 2030, 7.2 to 9.7 gigatons. When we take a distribution and look at what the overall emissions portion of that is, excluding the sinks on the bottom, you do see that the distribution is quite broad. And when we look at kind of what we haven't covered in the conference today, about 55% of our emissions are still left to be treated. And that's kind of my goal for the next hour here, to walk through kind of what some of the parallel conversations might have been in a similar conference running alongside this one. If we think about kind of the overall levels of abatement that McKinsey identified in our report, while it's about 55% of the overall emissions, the sectors that we haven't covered here do represent only about 40% of the total opportunity that we identified. Different reasons for that. One, obviously, being the addition of forestry as not an emission sector, but a sink sector. Also, there is, particularly within the industrial and waste sectors, there are very strong economics that help drive rational behavior that captures carbon more efficiently, assuming that, it's priced into the system, and or in particular, there's a strong enough signal around fuel costs that quite rational behavior does indeed develop. If we kind of take a fillet and look at another distribution of these opportunities, you can see on the curve here that we are going to cover a broad range of opportunities at different price points, ranging from the negative cost options, very much within the energy efficiency around automobiles, as well as issues in industrial sector, and then up to the higher cost areas that are in the agricultural space and some of the exotic technologies around CCS, et cetera, within the industrial space. So I'm going to walk through each of these in turn. We'll start with transportation and just offer kind of a few perspectives on that. Okay, no, that's fine. Let me, that. Yeah. Okay, so I will stop wandering here. When we look at kind of the overall distribution of opportunities within the transportation space, the big options are one around replacing. So you've got the opportunity to decarbonize the fuel source, and we've got opportunities around cellulosic biofuels. In our mid-range case, which would have corresponded with a concerted action case that Ken talked about yesterday, we see roughly 100 gigatons, or 100 megatons, I'm sorry, of potential opportunity there. Could expand out quite substantially depending on what you believe around technology evolution. I'll talk about that in a little while. There is a piece around how do you decarbonize or think about the efficiency of the drivetrains and the fuel economy of cars. That constitutes here roughly 200 megatons of overall opportunities. And these are the fuel economy packages that I've highlighted here. Primarily, these are negative cost opportunities, meaning that the net impact of pursuing them on the economy, if you take it from a total life cycle perspective, would be positive. But there are clearly issues around agency in terms of the duration and length of ownership of vehicles, et cetera, that may not create the incentives for people to go after them. There is a kind of the opportunity to move to additional new technologies, in particular around plug-in hybrids that could constitute an additional abatement opportunity. The challenge here in particular around plug-in hybrids as we go forward is that their ability to reduce carbon is a function of three things. One, the overall carbon intensity of the fuel source. So as we push on biofuels in particular, that's going to minimize or mitigate some of the benefit that you see from plug-in hybrids. Two, of course, the grid carbon intensity. And three, very tightly linked to battery efficiency. Hence, particularly prior to 2030, we see kind of more limited opportunities on the plug-in hybrid front, As we decarbonize the grid to a much greater degree, though, it's quite likely that that could emerge as a very strong technology in terms of overall carbon emissions technologies. There were other areas within the transportation sector. In particular, when you look at air travel, it does constitute, a large percentage of our emissions, roughly 2%. The challenge, or the airline industry in and of itself is actually quite focused on fuel to begin with, as you would expect, because it is a primary cost driver there. And more of the opportunities in that front have to deal with how exactly we manage the operations of aircrafts within the flight control system, thinking about limits on ascent to altitude, et cetera, that can help greatly reduce the amount of fuel on a per vehicle basis. And then, thinking about as well other options on air conditioning and other systems that are related. But this gives you kind of the broad slate, large negative cost options on the fuel efficiency and cellulosic front, and then, on the plug-in hybrids and other categories are going to be in the positive realm in terms of overall costs. If I think about kind of some of the key messages here that you want to think about and focus on, for biofuels, clearly, as was accentuated yesterday in the course of the discussion, cellulosic, non-starch-based fuels are the way to go in the end, that the fuel-food trade-off is one that clearly is not one that we can win. Nonetheless, we do see that there is the potential to grow the biofuels up to roughly a 20% of the total fuel pool by 2030 in our most aggressive case. That would require significant technological and capital deployment hurdles to be overcome in order to make that possible. I've already talked a little bit about the fuel economy measures, and we'll go into that in other detail. One big piece that's out there, right, that we haven't solved yet, and we're kind of the thinking is quite early on, but is this demand side management and consumer response piece that takes many forms, from direct price signals to individuals in the form of congestion pricing, thinking about pay-as-you-drive insurance, things like that. Smart growth is one that looms out there as potentially a necessary component, but one that's harder to place a pure carbon benefit on because it relates to so many other issues around lifestyle and kind of living conditions. And I've talked a little bit about the airline sector. So these kind of lays out some of the key takeaways. I want to just give you a snapshot or a few vignettes of the analysis that we've done. First, and here I'm going to, again, test your ability to read, but I'm thankful for the high-resolution screen that we have here. But you do see, that in the 2030 timeframe, the majority of our emissions are on the passenger front. The majority are coming from gasoline, and that's the real challenge. The primary driver of this is the fact that between now and 2030, we are going to add about 70 million people to the economy, but we're also likely to add on the order of 100 million cars to the economy, and that is the killer, that we're actually adding more vehicles on a per individual basis, and that trend seems to continue even though the mix of vehicles may be shifting from the light-duty trucks more to kind of crossovers and smaller vehicles here relative to kind of recent transitions. But that's a core issue that needs to be overcome. Fuel economy is one that clearly has been languishing here, but that the Energy Security Act from last year has done is going to have great impact on in terms of overall ability to address this. When you think about kind of the transportation sector, it is a highly independent link, and I'm talking specifically here about vehicles, where you've got a combination of impacts that are important to factor in that range from the carbon intensity of the fuel stock through to how many vehicle miles are traveled, onward to kind of how those miles are traveled, so the amount of idling time, the acceleration pace, et cetera. You can think then about how do I structurally kind of put in, embed energy efficiency in terms of the overall fuel economy packages of those vehicles, and then can I substitute, in addition to fuel economy packages, can I use alternative technologies in order to gain to a higher achieve a higher level of efficiency. Based on, some of our analysis and kind of our mid-range case, we see that over that supply chain, right, thinking about the carbon chain there, that about a 30% reduction is realistically achievable here in kind of a concerted action case in the 2030 timeframe. Obviously, many of those numbers can move quite dramatically depending around the amount of political will that we exert against it, but it gives you a sense for kind of the order of magnitude that we're at, again, using existing technologies. So I want to deep dive in a couple critical areas, and certainly one is around this issue of cellulosic and thinking about, what exactly is achievable on this front. And very similar to the last chart, which laid out the value chain within the transportation vehicle stage, you can see quite clearly here in the cellulosic or biomass production process, there are discrete steps as well, ranging from the actual biomass production onward through to the actual abatement capture. So you've got as we think about that value chain and what kind of some of the key constraints are here, on the biomass production front, if we're able to decouple from the fuel, from food as fuel, right, which is highly dependent upon us achieving, higher yield levels within our current cellulosic biodiesel or other alternatives. We do see that it's fundamentally not a land issue, at least for the next 25 years or so, that the U.S. does indeed have enough land capacity in terms of marginal pasture land, in terms of potentially bringing into service some of the conservation research or resource lands, and by our analysis would suggest that roughly 80 billion gallons would be a cutoff before we get to a point where we need to either dramatically improve our overall technology yields, or we need to, kind of expand the potential playing space and start cutting into some of the lands dedicated to either fuel or food or livestock production. On the biofuels front, in terms of the overall production, it's a question around engineering, procurement, and construction capacity constraints and how quickly we can put these plants up. There still is quite a bit of technology proving that needs to be done. Right now, the Department of Energy has its kind of 6 pilot plants that are here in the United States, and there are about 20 globally that are refining the cellulosic process. But until we achieve scale, it will be difficult to kind of yield the levels of, thank you, the levels of capacity in the near term, and hence kind of the research and development in terms of large-scale capital projects is kind of, or the deployment challenges around large-scale capital projects is a key constraint here. If we were to dedicate just the amount of energy to cellulosic in the end that we're currently achieving on the starch front with corn ethanol, you'd see roughly 1.1 billion gallons a year of capacity added in terms of overall cellulosic. If we achieve it in line with kind of pooling both refinery as well as starch capacity, we get up in the order of 4.4 billion gallons per year of additional capacity at the high end of the range. There's a question then around distribution, right? When you think about building out a biofuels chain, the question around distribution is really linked to what exactly are we shipping around. There are certain types of biofuels that can work within our existing pipeline infrastructure, and hence things like biodiesel and biobutanol are kind of favorable and pushed for that specific dimension, although the yield rates are not as high. Cellulosic, which seems to be the most promising in terms of cellulosic ethanol, which is the most promising in terms of near-term biofuels, really suffers and is constrained by the fact that it requires a completely alternative kind of distribution system. In the end, when we run the numbers on that, we see it's roughly about a 10% adder in terms of the overall cost at the end delivery. When we actually sum all this up, you get to a level of abatement where we see, kind of the potential for roughly 30 billion gallons of biofuels here in the 2030 timeframe as being our mid-range case. And that would equate to, again, about 100 megatons of overall reduction potential. And that's kind of depicted on this chart here, which shows on the left-hand side what the white is just the kind of the starch composition. The light green is the cellulosic composition on the right-hand side. And on the left-hand side, those three represent our kind of high, medium, and low cases in terms of overall penetration by 2030. That's on an overall fuel pool of roughly 300 billion gallons in 2030. So that gives you, again, a sense for the order of magnitude that we're talking about. The high green case there would correspond with about 20% of overall vehicle fuel pool. When you think about kind of the issues on fuel economy packages, there are a variety of technologies that exist out there. You know, some applicable to gasoline engines, some applicable to diesel engines. You know, there are a common set of things that you can do around lowering the rolling resistance, you know, improving weight, improving aerodynamics, et cetera, that would be broadly applicable across the value chain within vehicles. The real challenge is optimizing against what the customer wants and the performance levels that need to be achieved. In order to do that, you really need to group these technologies in overall economy packages that trade off against the performance criteria to ensure that you aren't double counting. When you start to do that, you see that there are, you know, kind of different discrete sets that come in at different price points in terms of the percentage reduction that can be achieved relative to the upfront investment cost in the overall vehicle. And I've kind of laid that out in a piece. In three big pieces here so you can get a sense for the overall trajectory. A key driver here is around hybrid technology and the fact that hybrid technology in and of itself is not fuel efficient, or is fuel efficient but is not at the most economic portion of the fuel efficiency benefits that you achieve. And hence, you know, when people think about a Prius as being extremely a fuel efficient choice, it is oftentimes the attributes that are not related to the hybrid, so the reduced rolling resistance, the improved aerodynamics, et cetera, the reduced kind of additional electronic load that all makes that car more efficient. And when you decouple that, you actually find that hybridization is quite an expensive abatement option, and that is kind of borne out on the curve in terms of where it ranks on the right-hand side. But that's something to keep in mind. That clearly when we think about kind of overall abatement options, there is a strong set that are not very expensive that don't require kind of shifting completely to a new drivetrain technology in order to achieve. So when we kind of look at the overall curve and where things pan out, you do see that there is you know, a fair amount of opportunity, and this is restricted obviously just to the transportation sector, a fair amount of opportunity in the negative cost area that is tightly linked to the deployment of fuel economy packages. In a few select instances, you'll see where plug-in hybrid and dieselization makes clear economic sense, but to a large degree, the hybridization falls on the right-hand side based on end use. So that gives kind of a few of the key components, again, around the vehicle and kind of drivetrain efficiency. You know, clearly, when we think about kind of the overall barriers, there is the consumer willingness to pay, you know, issues around the ownership period in terms of the fact that you know, the average vehicle owner owns a car for 4 to 5 years and may not even own the car, may be leasing the car, versus the life cycle of that vehicle is typically between 12 and 15 years. And the fact that hence fuel decisions oftentimes don't play in terms of the full life cycle benefit that you would achieve. There are personal payback expectations that are tightly linked to that in terms of wanting to achieve, each of us wanting to achieve our payback within the time frame that we're going to be the discrete owner of that car. There are also vagaries around the fact that people tend to peg on what the current gas price is as opposed to what the expected long-range gas price is. So just as people are focused right now on moving into more fuel-efficient vehicles, were it not for kind of ratcheted standards or CAFE standards that continuously increased our overall fuel efficiency, there is a demonstrated tendency to revert back to kind of previous tendencies there. Cellulosic technology, there is an innovation issue around making sure that the enzymes do develop at a rate that supports kind of its maturation as a technology. There is a production scale question around enabling the efficient deployment of capital there, and in particular, as we think about the proliferation of individual sites, siting and permitting, particularly in areas that aren't traditionally, centers of regional centers of development, because these are oftentimes in farmland where it isn't necessarily linked to rail, et cetera, become significant issues. And then on the hybrid front, there's a clear issue around battery development, a clear issue around the grid decarbonization, and particularly as you start to talk about vehicle-to-grid technologies, you need to have the supporting transmission and distribution infrastructure to take two-way traffic, which is an important element. So those again might be some of the key themes that you would hear coming out of a discussion on transportation from a parallel session here at another conference. If we flip over then to the industry and waste sector, from an overall kind of availability perspective, there is a significant challenge and a significant opportunity within the industrial sector around non-CO2 gases, and in particular these would be focused on methane, HFCs, PFCs, and then nitrous oxide, in particular in the production of adipic acid and nitric acid, as being very large but concentrated opportunities. There is some opportunity for carbon capture and storage, in particular, if we do move in the route where we're thinking about coal to liquids type technologies, it would be a necessary component of making that work. And there are select areas in the country where the power demand is high enough that it would be required on an industrial site basis in a cogeneration type application. There's quite a sizable opportunity around combined heat and power in terms of being able to integrate in waste heat recovery to the power production processes on a site-by-site basis. This is distributed quite differently. There's a large portion that kind of exists in the 5+ megawatt range, which is concentrated in a few of the key industries, but then there's a highly disaggregate piece that is distributed across many different sectors, and it is in particular concentrated within the food industry in terms of additional opportunity that exists there. There are clear process and product innovation potentials that exist across the chain. I think if I had to kind of characterize the challenge within the industrial sector, it is the fact that it is a highly fragmented market with many different levers that you would have to pull and kind of few opportunities to aggregate. Now, there are a few opportunities to kind of aggregate. When you think about kind of the key messages that I want you to take away or from a discussion here, one is that despite the fragmentation, there are a couple key pieces, and this would be in particular electric motor systems, and in particular combined heat and power, which do span uniformly across many of the different industrial sectors that we have here in the country, and that we could unilaterally kind of go after at a national level and potentially highly leverage it. There is, again, highly concentrated when you look at individual industries. There is a large portion in a small fragment of industries where it's non-CO2 gas related. So methane management largely falls upon the mining sector, and thinking about methane losses during the mining of coal, as well as losses in the pipeline infrastructure. And so there are ways to kind of manage and help kind of drive for efficiency and scale there. The challenge is, though, on that other 80% of the CO2 opportunity, though, it is highly disaggregated, and that's where kind of the challenge lies in terms of trying to get the scale for the level of impact that we're trying to achieve here. On the waste side, a much more positive story in terms of where our starting point is, largely because of a landfill rule that was enacted several years ago. You wind up in a situation where most large landfills have capping systems in place and actually recover the methane or at least flare it in order to minimize the CO2 impact. There is a larger opportunity around the smaller landfills that exist out there, and that would, is one that would need to be kind of managed in terms of an infrastructure basis on a site-by-site level. A little bit harder to get at because you're not dealing with, by large part, the big players out there. You're dealing with more individual municipalities and one-off kind of landfills. But there is the ability to kind of expand the tranche of activity there down to a smaller scale kind of landfill that actually does contribute substantially to our CO2 emissions. So those are kind of, again, the key priority points here. So a few pages of data just to back up and illustrate and provide some color to the discussion here. When we think about this issue of fragmentation, clearly illustrated growth on the right-hand side, or on the left-hand side, about 0.9% at an economy growth rate here, which is somewhere between 1.4 and 1.9%, depending on kind of which case you look at. But clearly lagging because of the migration of many of the heavy industrial sectors to other developing countries, et cetera. And another piece is the transition of the United States to more of a service sector orientation in the process, where this becomes kind of overall indirect emissions costs associated with it. But on the right-hand side, you get a sense for the challenge around fragmentation, where you've got a few industries, chemicals, refining, mining, and petroleum systems kind of being the primary focus, and here offering the most concerted opportunity for us to focus from a policy perspective in terms of trying to make a dent in the challenge. But you move from there into a series where it becomes much harder in much more disaggregated industries to actually intelligently prescribe policies that incorporate and encompass large chunks. And it's that 29% in particular there in the other category, which spans about 24 other sectors, which is the most challenging to actually manage. And again, if we're thinking about kind of reducing dramatically to the point where we're at 70, 80, 90%, we can't afford not to go after that in some way. When we think about kind of overall industry opportunities, this just kind of lays out how we tend to segment them. So there's energy efficiency pieces. There are elements of kind of being smarter with your waste heat and using combined heat and power applications. There are elements for introduction of process and material innovation. And then where applicable, there's the opportunity to think about carbon capture and storage in terms of overall integration. And this is, again, would only be applicable at very large scale industrial sites. As McKinsey kind of went through the analysis, we applied this kind of on a sector by sector basis in order to help understand, and this just gives you a sense for kind of the level of detail, and even within the operational improvement and process and product innovation, there were multiple levels of kind of different technologies and different opportunities that we looked at in terms of aggregating up to the overall potential. This page is more from the perspective of trying to educate on the level of detail that's required, and this is still at a high level in terms of overall trying to manage and attack individual opportunities within an industry space. But at the same time, you can see that there are clear opportunities that are identifiable where policy support and or prescriptive action can help focus industry activity and make appreciable dents here. This is another page that starts to look at kind of the overall opportunity set on the motor side. Again, this is one of the aggregated pools where you're looking at a cross-cutting potential. And what you see, is that strikingly, in terms of the indirect use within the industrial sector, about 63% of the indirect energy use, so the electric power consumption within the industrial sector, goes directly toward motors in and of themselves. So you have a highly leverageable opportunity here that you can potentially, by setting standards, et cetera, you can potentially kind of have a broad-ranging impact upon the economy, and that leads to the abatement potentials that you see on the right-hand side. Okay? So when you start summing all this up in terms of overall the electrical abatement potential, just looking at the impact on power, you do see that there is a large tranche, again, within the industrial sector that does come in at a negative cost or a positive return opportunity set. In terms of overall distribution, about 63% of that is focused on the more efficient use of waste heat. There is a large piece, about 15%, that's in electric motor systems, and then 22% is in other processes. So those, if you had to prioritize and think about the issues where you have the highest leverage on indirect emissions, combined heat and power and electric motor systems would be kind of the two keys there. If you expand out and you start to think about now, what about primary emissions, and start to think about as well kind of all the different options that we have and convert the electric power to a carbon footprint equivalent, you wind up with this cost curve, which gives you, again, a sense for the distribution. You do see on the right-hand side here some positive costs start to appear on some of the methane management systems, et cetera, which are a pure cost to the business in terms of kind of eliminating and reducing some of the emissions losses along pipelines, within coal mines, et cetera. Okay, this kind of gives a fillet, again, just so you get a sense for the distribution of opportunities, indirect, direct, across sectors and across gases, where the opportunities are concentrated. One quick, on the waste front in terms of thinking about the overall level of challenge here. This just deals with human waste, in particular, and you can see waste emissions constitute about 3% of our overall emissions levels. 72% of those are related to landfills. The vast majority of that, again, is covered in large landfills, which already have policies to at least capture the methane that's being emitted and ultimately flare it or use it for small-scale electrical applications. When you look at kind of the overall costs of the different options that we have in the landfill front in particular, which again is the largest opportunity set, it does range from, in cases where it's possible to capture at enough scale to get a return on an investment for a small kind of generating facility or providing directly to a customer, you do see the range somewhere between -10 and $10 per ton. There are additional opportunities as well on composting and capping, which are a little bit more expensive in terms of overall methane management. So when I think about, again, kind of the issues for the industry and the industrial sector to address, there is this issue of fragmentation, which is the highest, and kind of most pervasive one that we need to overcome. There are risk factors as we think in particular about the large opportunities around combined heat and power and other applications there. There are risk factors related to commodity price volatility, right? When you think about the willingness for someone to invest in a combined heat and power system at a time when natural gas is likely going up, there are incentives there within the system that create a little bit of drag on making those decisions. Clearly, this is a high value add from if we had to prioritize where our natural gas goes within the economy in order to minimize kind of emissions, it is far more favorable for us to place it here within the industrial sector than to build combined CCGTs, for instance, right? If we think about optimizing our carbon footprint around individual commodities. In terms of other factors, there's clearly an opportunity cost issue here when in the industrial sector. When you think about the resources required to go after this disparate set of opportunities that are out there, first off, there's a manpower constraint. Fundamentally, though, there's a capital constraint in terms of the willingness of individual companies to invest in efficiency relative to the opportunity to actually create markets and grow the business elsewhere. And our kind of prevailing mindset here in the United States tends to favor the growth aspect rather than the efficiency aspect in terms of how capital management and decision processes often run. And then finally, there's just an issue around awareness, and in particular, this is around larger companies tend to have energy management groups, but as you get into the more disaggregated opportunity set that's highly fragmented throughout the economy, there's a broad scale level of lack of information, essentially, to know what to do. And so the education process would be a key element of reaching out and creating kind of the momentum that's required there. Just a few thoughts on agriculture, which will kind of wrap us up here. Three big opportunities in terms of agriculture. One is around conservation tillage related to actually sequestering carbon in the kind of the roots and the subsurface material biomass. There's a second one around winter cover crops, which is actually kind of preserving and capping the emissions during off-season time so you don't get losses, and that helps kind of the ground retain its overall carbon composition. And then there's another opportunity set specifically related to, as similar to on the human side, you had landfill waste. You also have kind of waste on in particular, highly concentrated in the swine and livestock areas, and manure management there can be an appreciable, significant opportunity. So you look at it in terms of the key messages here overall from again, synthesized view. Soil management practices are the largest piece. The key issue here, though, is that this is it's a one-time opportunity that you get by kind of accruing that carbon within the soil once, but once you've got it there, it is, it's kind of fixed and it's not going to grow any further. And you have the question around impermanence, where if you use kind of low-till, no-till practices, you successively over, roughly a 5 to 7 year period increase the carbon content within the ground, but that can very easily be released if you go back to, kind of prior tilling practices. So monitoring and verification, and the ability to manage that permanence is a key issue. There is a significant piece around the livestock, about 40 megatons of overall opportunity. There are additional soil management practices that you can apply, split application of fertilizer, so you actually, split it half and half in order to ensure that kind of the overall runoff is minimized is a key area there. And then, some opportunities in particular around manure management system and electricity generation on larger scale swine and dairy cow farms. In terms of looking at the overall emissions side of things, right, again, a distribution just to give you a sense for where the emissions are coming from, because in order to manage, we need to understand that piece. A big chunk is on the agricultural soil management. There is the enteric fermentation, which is obviously the off-gassing, et cetera, from livestock. And then manure management, which is kind of the post-process there. A couple, charts again, just to give you a sense for where the overall gains are, and this looks specifically at the offset side, so thinking about tillage practices and winter cover crops and their overall impact, we see that we could roughly quadruple the overall resident carbon within the soil that's currently in use if we were to adopt these practices in the 2030 timeframe, before the 2030 timeframe. It is, when you think about where this opportunity lies, it's highly regional dependent, and not surprisingly, kind of the prairie states and the Midwest dominate in terms of the overall benefit from these types of practices. So as you think about kind of the implications of market development and internal offsets within the United States here, you have to think about the flows of capital to this particular region and how exactly you manage the diverse sets of stakeholders that would necessarily be involved. On the manure management front, thinking about kind of the opportunities there, very similar to the opportunities we had on the landfill side. You do see that, concentrated quite heavily within a couple different sectors. So the swine and the dairy sectors are the ones that we'd want to focus on first in order to actually make maximum impact on overall methane emissions. So, summary here on the agriculture front. Again, opportunities are widely distributed, in this case, across a broad range of stakeholders, because you've got local landholders, farms, ranchers, et cetera, that are going to be involved from an overall perspective. And so that complicates, it's highly disaggregated and highly decentralized, which is the real challenge there. Monitoring and verification is at a premium, in particular because of the impermanence issue. Also, you do have issues around leakage in terms of moving activity from one geography to another and being able to track that effectively. And there are very real issues around how exactly different crops and different livestock segments react and uptake carbon over time, et cetera. Managing that is managing that and creating kind of the equivalence and kind of trading mechanisms that would make that possible are quite challenging. And then the timing relevance, in particular around the soil options, is a real question, challenge, and opportunity here, because if you think about one of the benefits of soil sequestration is it is, a relatively short time frame option if we were to get it going that could provide us a quick uplift and a quick carbon benefit in the near term as we sort out some of the longer term technology issues, et cetera, in other sectors. So that's kind of, again, quick, high-level synthesis with a few interesting tidbits from the different sectors that are there to pique your interest and kind of encourage the dialogue and discussion here. I'm going to stop and offer, an opportunity for us for you to ask me any questions.